and then now it's people increase the, now you can see the participant, Professor. So
I'm
they're
ready.
coming. Yes, just a second. Okay, we have 17. How many people will be more? Do you know, Judy, how many people will come more?
Right now we have 25.
25.
It's increasing, the numbers are increasing.
Yes, we can wait for some more time. They are increasing number, yeah?
Yeah.
All right, that's great. So keep increasing number, Professor. Everybody is waiting for your presentation. We have 40 people now, almost, yeah. So we can start. Okay.
I'm ready to go when you tell me.
Yep. So thank you, everybody, coming to the session 4A, Resources Recovery from Brine. I'm very happy to introduce this session. So we have 4 presenters, including the Professor Enrico Drolli. And then we have a little bit of a technical issue because his video and the presentation sharing is the problem from his computer. So we will just listen to his voice regarding the his presentation on membrane engineering for extraction of strategic mineral from the ocean. So please join me welcoming Professor Enrico Drolli. So Professor Drolli, please, when you're ready, so you can start.
I'm ready.
Yeah.
I apologize. I'm very sorry for this incident. There is something wrong on our video system here. And so I will just give my presentation with no slide, but everybody interested, send a message. I will send these slides to Professor Sean. So if anybody is interested, ask him or ask me, and I will send you the slides. So what I was going to talk you is the situation today, from my point of view, in desalination. Maybe some of you already have been listening in the past few months, one of my presentation. I'm just repeating some of the concepts, which I'm assuming are quite important, interesting today. Everybody is very familiar with the problem of water shortage. So we are under water stress already, and this is a problem that you know will continue in the next decades without any question. There is no question of this. We have to face the water stress. However, in terms of innovation, in terms of research activities, a lot has been done in the last 20, 30 years. Very successful. Membrane engineering is today a dominant technology in desalination. If you check on the data in the literature, on the slide that I was supposed to present you, you will see that already approaching about 80% of all the fresh water produced on Earth is produced with technology related to membrane engineering and basically to reverse osmosis. Thermal system, the traditional thermal system are basically disappearing. No new plant will be realized in the next decade. The only investment will be on the maintenance of the existing one. But basically, all the fresh water produced on Earth in the next few years will be done based on membrane technology. However, if you check the situation that we have today with these interesting plants, these plants are going to be huge plants, by the way. Already now, we have a plant of the size as a Sorek of 627,000 cubic meters per day. And the new plant under construction, already designed, and some of them already under construction, are approaching the 1 million cubic meter fresh water produced per day. So huge plants are in progress. However, and that is all around the world, by the way, is in the Middle East, is in Australia, in the States, in China, etc. However, if you check the properties of this big RO plant, you will see something that will attract your attention. Everything is interesting, well done, but still we have limits. For example, recovery factor in all this plant is of the order of 50%, a little bit more, a little bit less, but order of magnitude is only 50%. So we are losing 50% of our water as a retentate. And another problem which exists in all these plants already in operation is the problem of the brine disposal. What to do with the concentrate? And normally, in some plants, for example, the one I was going to show you here in front of me, you have blended with cooling water, or just back in the ocean, or something similar, but is a problem. Problem, and that means also is a cost. And so something has to be done on these things, because if you are looking at the situation with the growing of the number of the plants around the world, for example, the possibility to discharge back in the sea is going to be legislation will be more and more severe, trying to avoid this, to avoid the problem with this, just destroying the bottom of the oceans. So with something has to be done. And today, this approach is what is changing. These problems are what are going to be significantly changing in the years. As I was mentioning before, you can find some interesting review by Masaru Kuriara from Toray, confirming what I was mentioning before, that in the next decade, big plant, the one, for example, in Hal Tavela, will be all RO, and they are going to have capacity of the order of millions of cubic meter per day of freshwater production. And there is no evidence of other technology competing with this. However, if you are just looking in terms of what is happening in terms of research, you will see that the situation is changing. There is a new methodology, new technology appearing, trying to overcome the limits of reverse osmosis, of the osmotic phenomena. And these new technology are based on membranes very different from the traditional one that we are using in RO. They are no more hydrophilic membranes. They are no more dense membranes. They are microporous hydrophobic membranes. And the operation that is going to be developed with these membranes and attracting the attention of a lot of research all around the world is membrane distillation. Membrane distillation is a new opportunity. It's a thermal system, by the way. It's a thermal system, so don't expect any significant reduction in principle in energy consumption. If everybody is telling you that you have new technology, membrane distillation, that use less energy, is a mistake, cannot be done. Or you have to understand the detail. Membrane distillation has some very interesting properties. First of all, the concentration of the transmembrane flux can be still present also for very high concentration of the retentate, of the feed solution. That means concentration polarization phenomena, which are the limits of RO, are not significant, don't affect significantly driving force in membrane distillation. And that means you can concentrate as much as possible, if you are interested, the feed solution, increasing recovery factor, and eventually doing something more. You can approach on the feed, on the retentate side, a concentration approaching the saturation of the salts present. That means you can induce a supersaturated solution, which means that you can promote an heterogeneous crystallization, basically. And that can be quite interesting in terms of solution to the brine disposal problem. Another interesting properties of membrane distillation is that it requires much less as a thermal system, as I was telling you, but it's much less energy is requested, which means you can operate also at low temperature. You can operate not only very high temperature as in traditional MSF, etc., but also a relatively low temperature. You can increase this membrane surface if you want to increase the overall productivity. And that means you can use the solar energy as for warming up your water. You can use any waste heat available in the system, etc., etc., which means you can redesign the desalination of seawater using a technology that will probably not substitute RO, but can integrate RO when RO is becoming less efficient. For example, approaching 50% recovery, and that means that the osmotic phenomena will kill your process, will reduce the transmembrane flux completely. You can at this stage operate. And in fact, what has been done in the years and what is in progress now, there are different situations which if you can introduce, that's what we made with the Medina project in Europe, this membrane distillation to operate on the retentate of the RO process, or eventually to the retentate on the NF process if NF was present in the pretreatment to RO. It's interesting that if you check the situation in terms of scientific contribution, you will see that membrane distillation in the past century, in the 1990s, etc., there were the level of publication were 10, 15, 20 papers per year. Starting from the 2000, we have a exponential growth. They started from 2000 to 2020. Now, 2020, we are publishing on the open literature. You can find publication of the order of 700, 800, 1,000, probably 2021. So an exponential growth compared to what was happening in the past century. And this exponential growth is mainly related to the interest of using membrane distillation in just in desalination, overcoming, as I was mentioning before, the limits of the osmotic phenomena. Basically, concentration independent operation, complete rejection of all non-volatile, possibility to use waste grade heat, and that means no pressure, that means less stringent mechanical properties of the membrane we are going to use, etc. However, something is very positive, but you have to take care of some other problem as the problem of thermal polarization. Thermal polarization is present in this system, and it can kill your process if you don't take care. So no concentration polarization, but thermal polarization. And if you are looking to this phenomena, that is already a limit. If you know some of the projects in progress, for example, in Korea, there's a significant research program sponsored by the Ministry of, no Ministry of Research, but Ministry of Industrialization, Forestry, etc. Just was showing you that the kind of using hollow fiber, the module you can realize as a length, not appropriate length of the module is no more than 48 centimeters. And that is related to the problem of thermal polarization, because the temperature profile will decrease with the length, and after 48 centimeters, there is no driving force anymore in terms of temperature. And that can be a limit in the efficiency for large scale units. 48 centimeters is not the most interesting length. However, this is a point which progress has to be done and will be done continuing with the efforts of research that we have in progress. This is you can find already open literature. and you will see that this number, if you have any better idea how to increase eventually the length of the module, that can be interesting, or how you can control temperature polarization. Why is important the problem of this increasing recovery factor? Is not only a question of the efficiency of the desalination, it's much more than this, because the water stress everybody is familiar with, but it's much more than water stress today that we have to solve. Mineral deficiency is becoming a severe problem, and this was already clear to the researcher years ago, but today it's clear to everybody. In Italy, if you want to buy a car today, you have a waiting list in some case of 1 year. And the reason is that there is the chips, the material necessary for all the electronic part of your car, etc., takes a lot of time. They are disappearing. So we have, there is a deficiency on the market, and prices are increasing. Time you have to wait is also increasing. During the last years, people are less aware. We have been losing something between 70, 50%, 85% of this percentage of mineral depletion all around the world in traditional place where we were used to extract the minerals. So something has to be done. And what is interesting, if you check the situation in the brine of the existing RO plant, you'll see that if we just look to the existing brine and we try to use this brine to recover minerals, in the brine are all the minerals that we have been using in the past decades, you can have significant contribution to the solution of the problem. For lithium, just extracting the lithium present in the brine of the running RO plant today, you can increase 30%. Magnesium, you can double the production of magnesium just by reusing the lithium present in the brine of the existing RO plant. So quite interesting from this point of view for giving some contribution to the solution of the problem. And in fact, big projects are in progress all around the world for trying to solve this mineral depletion problem. Keep in mind that the sea can be considered already as a liquid polymetallic ore. That can be an open sky mine system where basically a lot of minerals are present, and if we know how to extract them, that can be quite interesting contribution to the solution of the depletion of minerals. And the minerals, the membrane distillation that we have been mentioning before can really give a contribution, because as I was mentioning, in membrane distillation, transmembrane flux is independent from the feed concentration. So the limits of RO are not present. We can produce a supersaturated solution on the feed side, and the strategy is totally different than the one we are still using today. The new strategy is based on the logic that the overall cost of the desalination can be no more related to the cost of water you are producing and eventually selling, and that is a very low value. You cannot charge more, and people don't like to pay for the water. But you can do with just selling the products of the brine, of the mineral you can extract in the brine. If you go in the literature, you will find different examples of this kind of situation. We published different papers in the last years, and you have a new mining industry which under development for extraction of minerals from seawater. And that can be quite interesting and important innovative studies for the very, very next future. But the problem is more complicated than expected. It's not, if you try to extract, to develop this approach, and for example, for lithium chloride, you will realize that it's not so easy as expected. Lithium chloride is very soluble. By the way, when I'm talking of lithium is an example, but there are many other salts of interest rubidium, cesium, or barium, etc., with some problem that's similar to the one I will describe you now. For example, with lithium chloride, lithium chloride will approach the supersaturation. That means the possibility to arrive to crystallization only at about 14 molar. Now, if you make your experiments with membrane distillation, you will see that using traditional direct contact membrane distillation, it will be impossible to approach 14 molar. Already at 7 molar, about 6-7 molar, transmembrane flux is going to zero due to the polarization phenomena present. This is at wetting phenomena present. And that's something that is a limit. The problem can be solved. It takes some time to realize the situation, changing the configuration. And today, lithium chloride can be extracted by using vacuum membrane distillation. But this is a way of doing, and with vacuum membrane distillation, you have some benefits. You can realize the highest driving force that is in this MD system. There is no temperature profile on the permit side, and the wetting, you can minimize also wetting, etc. However, this is not enough, because there are other problems which still exist. We started to work on the possibility to extract lithium chloride, and we realized that with some membrane the system works, but with some other membrane the system does not work. For example, if you're working with polypropylene, you can approach a concentration 14 molar and you can crystallize lithium chloride. Crystallization is the best way to separate in a very high purity any minerals. And there is a lot of interesting literature in fractional crystallization without membranes. And today we have to realize to do the same with membranes. But cannot be done with polymers where fluorine is present. And the most traditional membrane people are using today in membrane distillation are fluorinated polymers, and SPVDF, etc., or Iflon. The system does not work. You have wetting. Strong wetting is always present, no way to crystallize. So that is something that has to be understood and solved. And it's not only for lithium. Remember that if the system works, is interesting, and you can find in our literature with paper already published, where you can, as I was mentioning before, calculate the cost of the operation, not more in terms of water cost at the end, but the total profit per year coming from the mineral that you are able to separate and to extract from the brine of the system. And lithium is a typical example. Now, if you want to understand a little bit more on what is happening, avoiding the wetting problem, we are working on this aspect, and you will realize what I was mentioning before. Fluorine can be at the origin of the problem. So you need today membranes with no fluorine present. And if you do this, can be ceramic membranes, can be polypropylene, can be other polymers, you can realize the crystallization of lithium chloride at 14 molar, and you can separate. Keep in mind that another important aspect, very interesting, that you have with membrane-assisted crystallization, with membrane distillation in running in the crystallization mode, is that you not only have crystals, but you can try to have specific final crystal habits. If you know the condition characterizing one of the possible polymorphs, and you can realize this condition, you will realize, for example, with magnesium sulfate, you don't produce magnesium sulfate. You can produce epsomite, magnesium sulfate with 7 molecules of water. With sodium sulfate, you don't produce sodium sulfate, you produce thenardite. That means sodium sulfate with no water at all, etc., etc. That can be.
We have 1 minute. 1 minute
yes,
left.
That can be a significant improvement in the crystallization step. For doing this, however, something more has to be done. We are working today, forget about the graphene, but we discovered that there is a large family of minerals that are running as the graph have a final crystal habits as graphene, 2D, all 2D minerals. These 2D minerals are the one attracting today our attention. We are working on hybrid membranes in which you can add to the traditional polymeric system, if possible, not containing fluorine, these 2D minerals as selenide, telluride, and similar, which has interesting properties in terms of thermal conductivity, not so low as PVDF, but not so high as graphene. And these minerals, when entrapped in appropriate polymeric phase, they can also minimize wetting and giving you interesting effect on the kinetic of crystallization. And that is one of the areas where people have to work. Let me approach conclusion telling that no, we need much more selective membranes if we want to operate in this to solve the problem of the extraction of minerals from the sea. Much more than this traditional osmotic membrane we have today. And for doing this, there is another suggestion I like to mention. I'm sorry that I cannot show you this slide, but in the past years, we have been working on these imprinted molecular membranes. Today, the possibility to realize imprinted membranes selective for lithium, for rhodium, for cesium, etc., is becoming again of interest. Can be done, and you can have some of these minerals which are also 2D. So all interesting properties of the 2D material, graphene, can be transferred to these, for example, thin telluride, bismuth, selenide, very unusual salts for most of us, but they work nicely, and a new membrane based on this material can attract the attention of researchers for contributing to solve the problem, not of freshwater production, well solved with traditional RO, but improving the performance of RO with membranes that will operate on MD integrated with the traditional RO system. I apologize that of the situation that I was not able to show you slides on this. Ask and I will send you all of this. Thank you for your attention.
Thank you, Professor Drolli. We have one question for you. So you are talking about the kinetic of crystallization. How can operate on the large scale differ from the lab scale result in terms of kinetic of crystallization? So can you answer this one?
Sean, I lost it. Can you repeat the moment? I'm sorry, I lost the question.
So
tell again.
Alex, he's asking how we can make some scale up based on our lab scale kinetic of crystallization is different from the large scale. So how we
at
can,
the moment,
yeah.
No, the problem of the scaling up is the major problem we have today. No, the real problem that exists if you want to realize this integrated desalination system where membrane distillation and membrane crystallizer will play a significant role. The major problem is that at the moment we don't have membrane produced on large scale for realizing plant of the size similar to the RO plant. Only in Korea there was a big project that has been done, arriving producing at the end the pilot units with about 400 cubic meter fresh water per day. But these the hollow fiber membranes have been produced in this case. But today, at my knowledge, if you want to have this module, many of these modules for scaling up your system, not easy. So this is an area where we have to demonstrate more the potentiality of this approach, realizing large-scale plant for recovery of minerals from the sea, and the possibility to have somebody investing in producing all hydrophobic microporous hollow fibers for making plant able to operate on the same size of RO will become real. it will take, in my personal opinion, at least 5–10 years before we will have a possibility to scaling up and to realize this approach, which is the one of the most interesting for the future development. Keep in mind that I did not mention that when you are working this way, you can also combine the production of fresh water with production of electricity. I think Professor Sean also mentioned yesterday, and you can find the literature, and in some part of the world, in Middle East, somebody is already doing this. You can also produce electricity by using pressure retarded osmosis. And pressure retarded osmosis is giving you interesting way to transform chemical energy in electricity, the different chemical energy between the salty water and fresh water in electricity. And that is another interesting future for the desalination. So desalination will not only produce fresh water, will produce also fresh water in the future, but will in principle produce minerals, extracting these minerals from the sea, and electricity, extracting the same energy from the salinity gradients.
Thank you, Professor.
We need the membranes.
Yes, absolutely. So because of this time limitation, so we just want to end the great talk. Thank you, Professor. And then we can share the slide after this presentation. So thank you very much.
I will try to send you as soon as possible now.
Yeah, thank you.
Okay. Thank you.
Best.
Bye-bye. Thank you. Bye-bye.
Thanks. So next speaker is from Spain, so University of Cantabria. So Tamara Sampedrio. So she will mention about reducing the energy consumption in SWRO desalination plant. So please join me welcoming Tamara presentation. Can you share your slide, Tamara? Yeah.
Can you see my?
Yeah, that's perfect. Please go ahead.
Well, my name is Tamara San Pedro. I'm a PhD student who belongs to the Department of Chemical and Biomolecular Engineering of the University of Cantabria from Spain, and I'm going to present my work entitled Reducing the Energy Consumption in Seawater Reverse Osmosis Desalination Plants through the Implementation of Blue Energy. In desalination plants, the intake water stream with high salt concentration is separated into a freshwater stream and a concentrate waste stream. Moreover, the desalination process has associated an energy requirements that in case of seawater reverse osmosis, it has been estimated in the range of 4 to 6 kilowatts per cubic meter. In this context, the energy consumption and brine management have been defined as key barriers for desalination expansion. In this sense, there is the possibility of energy recovery from brines, contributing this way to the consecution of not only to the consecution of Sustainable Development Goal 6 related to clean water and sanitation, but also to Sustainable Development Goal 7 associated with affordable and clean energy. Salinity gradient energy, also called blue energy, makes possible to recover energy from desalination brines because salinity gradient energy generates electrical energy from the mixture of water streams with different salt concentration. To harvest energy from the released Gibbs-free energy during the mixing process, control mixing technologies are required. Reverse electrodialysis is the mainstream membrane-based electrochemical technology to harvest salinity gradient energy. In the full figure, you can see the operation mechanism of a reverse electrodialysis module. The module is composed of a cation and ion exchange membranes positioned alternatively by space when water streams flow along the compartments that exist between membranes, and ion flux take place generated as a consequence of the concentration gradient. The ionic current is transformed into electrical current by a redox reaction that occurs in the electrodes, producing this way electrical energy. Salinity gradient can be obtained from different water streams and different origin. River water and seawater from natural origin, and desalination brines, wastewater effluents, or even engineered solutions from anthropogenic origin. In this case, we focus on the use of desalination brines, which present several benefits in comparison with other water streams. Because desalination brines are high-quality water streams, so it is necessary to perform a pretreatment before the reverse electrolysis process, and additionally, desalination brines give rise to a higher salinity gradient, which provides better gross power generation. The following shows the gross power density results obtained using a mathematical model developed by the research group I belong to. And here we can see the comparison of different salinity gradients obtained using the high concentrated solution. For the scenario with seawater and desalination brines, the maximum power achieved is 0.3 watts per square meter. And for the scenario that uses desalination brines with wastewater effluents, considering the optimum concentration for the diluted solution, that is 0.02 molar, could provide a maximum gross power density of 2.5 watts per square meter. This second scenario, due to its high potential for energy recovery. Life 3E, a project that belongs to the European Life Program, promotes salinity gradient energy recovery, reducing thus a fossil fuel dependency in urban wastewater treatment plants and that we use for urban irrigation or industrial uses is this is a transnational event in which the Department of Chemical and Molecular Engineering.
Senta, mi deve fare un piacere, Stefano, qui l'ora pesta, ma io ho appena finito la presentazione lì, ma ho avuto un problema perché non sono riuscito a fare vedere le
Yes, let me.
qualcosa sul calcolatore che
this is
Professor cambiare video, un pasticcio.
Okay.
Allora vorrei però mandargliele.
Okay.
Quindi dato che non le avevo qui
Judy?
adesso, sullo schermo c'avevo soltanto quelle della preparate.
Can you close his connection, Professor Enrico Drolli? Yes, please. That's good. Okay, please. Sorry for that. And then can you go ahead?
Well, I continue. This is a transnational project in which the Department of Chemical and Molecular Engineering of the University of Cantabria is participating, and whose consortium is formed by different institutions, universities, and companies. To see a more project, you can visit our website, and here you have the link. And in this European map, it is the location of every treatment facility selected for the scenario that combines seawater with wastewater effluents that has been already studied in this project. And the main objective of this work is to select European Union site-specific emplacements for salinity gradient energy harvesting by means of reverse electrolysis in seawater reverse osmosis desalination plants located near to a urban wastewater treatment plant. Regarding the salinity gradient energy recovery process, as high concentrated solution, we are going to use desalination brines, as I've said, and as low concentrated solution, a secondary effluent that previously received a reclamation treatment. And when we put in contact these two water streams solutions in the reverse electrolysis stack, we can obtain reclaimed water, slightly more salty, but still with enough quality to be reclaimed, and salinity gradient energy. Taking into account the value reported in the literature for this type of energy recovery processes, using real water streams of desalination brines and wastewater effluents, it has been possible to generate 0.075 kilowatts hour per cubic reclaimed water. To perform the site-specific scenarios selection, a multi-criteria selection method has been established. Considering that seawater desalination plants are installed in coastal countries and reverse electrolysis performance is greatly affected by temperature, the coastal countries of the European Mediterranean region will be the most suitable for the implementation of this technology. In addition, been chosen to carry out this study because Spain is the European Union country with the highest desalination capacity. A second selection criterion, it has been considered the desalination plant location because the water pumping process is an energy consuming part in the whole process. So it has been established a distance to the wastewater treatment plant equal to or less than 1 kilometer with an altitude difference equal to or less than 10 meters. It has been also considered the wastewater treatment plant effluent compliance because we want to encourage and facilitate wastewater reclamation and reuse and optimize power production. So we have selected only wastewater treatment plants which comply with the European directive for wastewater treatment. And finally, the treatment because with higher wastewater treatment flows, we can produce a higher amount of energy. For the applied criteria, a total of 7 desalination plants have been found on the Spanish Mediterranean coast. The map shows the selection of plants. As an example, focusing on the desalination plant, you can see the aerial view, the seawater system, wastewater treatment plant at a distance of 6 meters and with an altitude difference of minus 40. And the following table, the main characteristics of the selected facilities, brine flow, wastewater treated flow, and distance between desalination and wastewater plants. Observing that the water flows ratio, except in one case, in all the cases the brine flow is higher than the wastewater treated flow. Therefore, the wastewater flow will be the limiting flow for the energy production process through reverse electrolysis. Shows the definition of the salinity gradient for each scenario study. Here we can see that brine salinity vary between 1.07 molar and 1.23 molar. And for the diluted solution, we have seen that in all cases it is below 0.02 molar. That is the optimal diluted compartment concentration that has been determined trying to find a trade-off between the salinity gradient and the low concentrated solution resistance. Finally, we have estimated the environmental benefits of the implementation of this technology, and considering the energy production of 0.075 kilowatts hour per cubic meter and the wastewater flow that is the limiting factor, it has been estimated that desalination plants could generate approximately 55,000 kilowatts hour per day of renewable salinity gradient energy. The production of this salinity gradient energy would reduce the fossil fuel consumption. So considering the carbon intensity of the electricity mix of Spain, this technology could avoid the emission of about 1,200 tons of carbon dioxide equivalent per year. And taking into account the total freshwater withdrawals of Spain and the total volume of treated wastewater that would be reclaimed in the selected wastewater treatment plants, the implementation of this technology would suppose a reduction of freshwater withdrawals in Spain of 0.65%, considering only the 7 wastewater treatment plants selected. You can see that there is a great potential for freshwater withdrawal reduction. And to conclude, as a preliminary study, it has been determined that Spain in Spain there is a great potential for salinity gradient energy recovery, using for that purpose a desalination brines and secondary wastewater effluents, and the Life3 project through the construction of a salinity reverse electrolysis prototype, the integration in a real scenario, and the demonstration activities that will be carried out over a period of 2 years will provide valuable technical information in order to upload a salinity gradient energy by reverse electrolysis technology readiness level and facilitate the future replicability in wastewater treatment plants, seawater reverse osmosis plants. And that's all. Thanks for your attention.
Thank you very much for the interesting talk. So we have one question from Carolina. She's asking question about each power density put it in terms of membrane pair area or membrane total area.
And the membrane area, it is referred to the membrane area, not to the per membrane area, to the total membrane area.
Total, all right. Also,
The results, here you are not referring to a pair of membranes in this case. In other results, in other works, maybe, but in this one, we are, I'm referring only to a membrane area, the total membrane area, not separated by a pair of membranes.
Okay, so Carolina, yeah, she understands. Also, yesterday, the Professor Seung-hyun Kim, who was our plenary speaker, mentioned about the PRO. Yep. And then I'm just wondering, if you apply PRO exactly same as SWRO and UWWT plant, so what's the difference between RED you compared your investigation? How about the PRO if you apply? So what's the difference between RED and PRO in your investigation?
I don't know about what are you referring. I don't know which is PRO, but
okay, my question is not in the question. My question is, how about PRO, SWR PRO, not SWRED? So what's the difference of the energy production? Have you ever investigated?
no, I don't know what you are referring.
Okay, what I'm saying
Maybe,
is
maybe
you investigated the SWRO wastewater treatment effluent using RED, reverse electrodialysis. Am I right?
yeah, but
And then
maybe
if we use
you are
the,
referring, we are going to in the project, the idea is to use the energy not in the seawater reverse osmosis desalination plant, in the wastewater treatment plant, so we can reduce more the energy intensity of this type of plants, because we know that in the desalination plant, this energy would be negligible compared to the energy consumption of this type of plants, of desalination plants.
all right. Thank you for your great talk. And then, yeah, we will have next speakers. Thank you, Tamara.
Thank you.
So next speaker is Said Muket Hussein. So he will talk about chief induced electron for selective lithium recovery from the CDI system. So Said Muket Hussein, if you are ready, can you share your presentation slide and you can start.
You can see the slides.
Yes, I can see that.
Okay. Hello, everyone. I am Syed Muqit Hossain from University of Technology, Sydney, and I'm pursuing my PhD under the supervision of Professor Ho Kyung Sean. And today, the title of my presentation is facile synthesis of GIF8-induced electrodes for selective lithium recovery from aqueous solution by using capacitive deionization system. So for lithium, the only way is up if you consider the demand. For instance, the electric vehicle demand will continue to drive the lithium market forward. Only the contribution of electric vehicle is expected to show a growth of approximately 35% by 2030. And add to that the growing demand from applications such as energy storage system, 5G devices, and Internet of Things infrastructures. To meet such substantially high demand, lithium production must quadruple by 2030, which was 345,000 tons in 2020, would have to be 2 million tons in 2030. So around the world, lithium deposits come in three main types. There are rock-containing lithium, clay-containing lithium, and salty water or brine that contains lithium. We can see an overview of the distribution on the slide. So conventionally, to get the lithium out of the rocks, you have to mine, crush, and heat the rocks, and then use various chemicals. Again, to get the lithium out of the clay, you have to dig it up and use various processes and chemicals that a number of different companies are working on, despite being massively energy intensive and detrimental to environment. Finally, when it comes to lithium incorporated brine, the conventional way is to pump the brine into huge solar evaporative ponds and let the sun evaporate the water, leaving the lithium salts behind. Although solar driven, these methods are slow, inefficient, and unsustainable. However, the process we are interested in is the direct lithium extraction technique, or in short, DLE. So as the name suggests, instead of using the evaporation, lithium is directly extracted from the brine while returning the water to its original source. These have several advantages over other methods, such as smaller footprint, efficient recovery in short time, and low operating costs. So how DLE works? Broadly, there are three types of DLE methods. There are adsorption, ion exchange, and solvent extraction. However, our proposed DLE is electroadsorption technique called capacitive deionization, which is an emerging desalination technique. As you all know, in this method, saline water passes between a pair of porous electrodes, which are usually carbon-based, while a working voltage is applied in between the electrodes, and the salt ions in the field flow migrate to the electrical double layers at the carbon-water interface, which performs the desalination. We plan to use this mechanism for selective lithium extraction. However, the bare activated carbon electrodes are not very selective towards lithium. And a number of past works claimed that a metal organic framework subclass called GIF8 can promote lithium selectivity by permitting only lithium to cross over. GIF8 consists of zinc metal and two methylimidazole ligands coordinated in framework structure. Herein, in this work, we plan to use a thin film of GIF8 on our carbon electrode to make it selective towards lithium. So here you can see the experimental layout of our work. So we did the experiments in batch mode. So this is our reservoir where we are taking the effluent out and putting taking the influent out and putting the effluent in and collecting our sample from here. And we used 4 types of binary model solutions. incorporating the competing ions with lithium like sodium, magnesium, potassium, and calcium. And for adsorption, we did the investigation for 20 minutes and followed by a desorption of 5 minutes at a voltage of 1 volt. And we maintained a flow rate of 20 milliliter per minute. So let's see some results. So you can see the SEM of a bare carbon electrode. It's a commercial one we have used, and we have coated this one with we grew G8 on our electrode. We grew in situ. Used a mixture of 1:75 molar ratio of zinc salt and the organic linker, and grew the G8 on the membrane for 72 hours. So at the right, you can see the final image. It's visible. The formation of the G phase is visible on the SEM image. We also confirmed the formation through XRD, FTIR, and EDS mapping. So you can see the dominant XRD peaks around 7.26 degree and 10.34 degree to theta. And the dominant FTIR peaks are around 421 centimeter, which is for zinc and nitrogen vibrations, and within the range of 1350 to 1500 centimeter is for the imidazole ring vibrations. So it's obvious that G8 was formed on our electrode. Now, if we see the performance results, like how it worked for the monovalent and divalent ions, let's see for sodium, how it worked for sodium. So at the left of the screen, you can see this result is for the bare electrode. So during adsorption, after 18 minutes of adsorption, the sodium removal was around 25%, whereas lithium removal was 19%. So the selectivity ratio was approximately around 0.7. And you can see the reduction in conductivity and the change in charge rate as the current flow. So how it changed while we used G8 coating for the monovalent sodium. So you can see the selectivity ratio increased substantially. It's around 4 in the right figure. And the lithium removal here is around 19%, and the sodium removal was around 4%. And as the ion removal decreased, so the conductivity ratio, the reaction in conductivity ratio is reduced along with the change in charge transfer. So how it behaved with potassium. So for potassium, the bare electrode, you can see at the left of the slides, the potassium removal was around 24%, and lithium removal was around 10%, and the selectivity was around 0.5, which was increased after the coating to 1.2, and the charge transfer rate reduced as the ion removal rate is reduced. So for you can see for monovalent ion, the selectivity increased. Which is favorable, which is very good. However, let's see what happened to divalent ions. There are many literature showing that with divalent ions, the G8 is like very established metal organic framework to enhance the selectivity ratio. So with the bare electrode, we see the magnesium removal of 35% and lithium removal of 24%, giving us a selectivity ratio of 0.6. But the problem is, after coating, we haven't seen much improvement with the selectivity ratio in case of divalent magnesium. So I will discuss later why this happened. But the removal decreased. As you can see, the magnesium removal is now 20%, 26%, and the lithium removal is 14%. And the conductivity reduction reduced, and the current flow reduced, And same phenomena happened with calcium. We didn't see much selectivity improvement after the G8 coating. So now if I talk about the mechanism, so what happened? However, in all the cases, we have seen the decrease in the charge transfer. So which gave us some idea about the mechanism. You can see, as with sodium, the monovalent one, we have seen substitutional increase in selectivity ratio. That means only lithium ion is passing through the G8 coating, and sodium is not. And which was evident for both lithium and potassium. But for magnesium and calcium, what happened? Although you can see the atomic diameter of magnesium and calcium is higher, the hydrated diameter is higher compared to lithium, but the selectivity ratio didn't increase. So what happened? Lithium passed through the G8 coating, but the calcium and magnesium, they possess like higher potential for van der Waals and Coulombic attraction. So even they couldn't pass through the coating, as our coating is very thin, like some fraction of microns, as it is only a layer of G8. So due to that secondary attraction potentials, and those are very higher compared to lithium and sodium in calcium and magnesium, they remain attached on the G coating. And the G8 channels, those are very small, like the channel openings are 0.34 nanometer. So even lithium at hydrated condition, like it is nearly 7.7 nanometer. So even at hydrated condition, it can't pass through. However, it is already proven that lithium can pass through the G8 channels through a mechanism called successive dehydration and hydration mechanism. So it gets partially dehydrated, and then it passes through the channel and then again hydrated. So this is the mechanism that that is happening there. That's why we have seen substitutional increase in selectivity ratio for monovalent one, but not with the divalent one. So what are the challenges and future perspective of this work? So we have seen dissolution of G8 coating after consecutive runs, as we have used just a GIF coating on the layer. And as we grew G8 on the electrodes, we faced non-uniformity. And we need comprehensive estimation of the Coulombic and van der Waals attraction-based absorption if we want to optimize the system. And future perspectives are incorporation and optimization of G8 with lithium selective cation exchange membrane, optimization of membrane thickness to minimize the Coulombic and van der Waals effect, and prevention of the dissolution of G8 during operation. So that is all from me. So these are the references I use. Thank you. Now, if you have any questions, please.
Yes, sir. Can you please stop the sharing?
Okay.
Yeah, that's good. So any question from the audience? Otherwise, yeah, we have one question from here. Could you comment the process of electroformation? Is G8 conductive material?
So as I mentioned, we just grew G8 on our commercial carbon electrode in situ. So we used our 1:75 molar ratio of zinc salt and the organic linker. And G8, I don't think G8 a conductive material. Even the channels are neutral. G8 channels are neutral. So that's why it doesn't have affinity for other ions. And due to that reason, lithium could suitably did the successive hydration and dehydration mechanism and passes through the GIF channels. I hope that answers the question.
All right. So thank you for the your answer. So if we don't have any more questions, so we can go for the next speaker. Thank you, Muket Hussein.
Thank you.
Okay, Judy, can you please play the video for the last
Sure.
speaker?
Yes, yes.
Do we have last speaker here? I cannot hear the voice. Can you share the sound as well?
Pleasure to be here today to talk about the recovery of water from high salinity streams through hybrid membrane systems. I'm going to divide this talk into 4 parts. The first part is a brief introduction to the different technologies available for water recovery at present. After that, I will explain the osmotically assisted reverse osmosis process in order to explain the sequentially osmotically assisted reverse osmosis. To finish, I will show an application of this technology. Firstly, I'm going to do a brief introduction. The shortage of fresh water is currently one of the biggest challenges and poses a threat to the growth and balance of all nations and their ecosystems. The desalination of seawater for human consumption and proper wastewater management is especially complicated in the case of streams with high salinity. Recent years have seen an evolution in thermal desalination systems towards membrane-based processes with the objective of reducing energy consumption. To this end, technologies such as reverse osmosis and its variants are the most prominent. However, it can only be applied to streams with a limited salinity range, and so it is used to reconcentrate the feed water before using thermal process. Among the thermal processes used for desalination of high salinity streams that can be treated by reverse osmosis, distillation, thermal concentration, or crystallization stand out, but all of them involve considerable energy expenditure, so it's necessary to develop a process that minimizes this consumption. Therefore, an opportunity opens up in the development of technologies that allow for recovering water from brines, which can treat current with higher salinity than reverse osmosis and at the same time suppose lower energy consumption than head treatments. These developments are of utmost importance for the advancement and implementation of zero-liquid discharge systems. For this reason, the incorporation of membrane-based technologies such as electrodialysis, reversible electrodialysis, forward osmosis, membrane distillation, osmotically assisted reverse osmosis, or high-pressure reverse osmosis have been presented as alternatives for the concentration of reverse osmosis reagents. In recent years, technical economic evaluations of the different technologies used for minimum discharge of air have been performed. Among the emerging technologies, forward osmosis is among the ones that have been the most developed. In this work, forward osmosis was determined to be the most efficient technology in terms of recovery and cost savings, as well as low energy consumption. In other studies, the osmotically assisted reverse osmosis turned out to be the most favorable method in terms of the price of produced water and the consumption of specific energy. On the one hand, as forward osmosis operates at low pressure, it results in falling layers in the membranes that are less compact and easier to clean than in the case of reverse osmosis. This reduces the operating cost for scale control and extends the applicability of forward osmosis in CLD systems to wastewater with high falling potential and can be incorporated as an emerging technology in the development of CLD systems. On the other hand, ORO is a variant of traditional reverse osmosis which allows water to be recovered from high salinity solution. The feed solution is introduced into the high pressure chamber of a reverse osmosis module. On the opposite side, a current flows counter current with a salinity lower than the feed solution, called the sweep solution. A difference in hydraulic pressure is established between the feed solution and sweep solution, which, when greater than the difference in osmotic pressure between the two faces of the active membrane layer, causes a flow of water. As can be seen, ORO could be an alternative to regenerate the diluted solution in forward osmosis. Now I'm going to talk about the ORO process, taking into account that the the maximum applicable pressure is limited in reverse osmosis, mainly due to the cost of pumping and the mechanical resistance of the membranes, the salinity of the solution that can be fed to a conventional row is also limited. However, if a solution with higher than salinity is introduced into the permeate chamber, the permeate osmotic pressure is no longer negligible, and the osmotic pressure difference between the solution and the permeate to be overcome decreases, as we can observe in the figure. Consequently, the necessary pressure can also be reduced. It can be verified that it is possible to process a feed with the highest concentration desired in a reverse osmosis unit and record the permeate water in a sufficiently concentrated osmotic solution. With osmotically assisted reverse osmosis, the same water flow as in a conventional reverse osmosis can be achieved by applying a lower pressure and/or feeds with higher salinity. However, because the permeate is mixed with the osmotic solution, the introduction of an osmotic solution requires a later stage to be carried out to record the pure water, the final product. This process is registered by the patent, which we can see in the slide. Let's move on the next point to explain a configuration of the water process developed in this work. The method for concentrating high salinity solution is made up of a single osmotically assisted reverse osmosis unit, tanks and one pumping system. The Suaro unit has a high pressure feed with a certain concentration on one side and a more dilute osmotic solution on the other side of the semi-permeable membrane. In a generic stage, the mass of water is transferred from the DI tank to the DI+1. To do this, the feed solution contained in the DI tank is pressurized to a high pressure and is passed through the concentrate side of the Suaro unit, where it's concentrated. The water is received by the osmotic solution, which is directed to the I+1 tank. In all stages, the concentration gradient between the feed solution and the osmotic solution must be maintained in such a way that the osmotic pressure difference between the feed and osmotic solution are less than the hydraulic pressure difference applied to these streams in the membrane unit, which will produce a net mass flow. The process continues sequentially at each stage. In the last stage, the draw solution with the lowest concentration is filtered in the conventional reverse osmosis unit. The reagent unit is recirculated to the osmotic solid deposits, depending on the concentration of the reagent cells obtained. In this sequence, the membrane of the Suaro unit is subjected to increasingly diluted osmotic solution, which causes a certain washing effect in them, improving their behavior. In this work, an application of the Suaro system has been developed in the framework of a seawater desalination operation for the recovery of water from the draw solution of a forward osmosis operation in order to estimate the membrane areas, operating times, flows, and compositions of the currents of the different stages using the engineering equation solver software. At the beginning of the process, the reagent of a conventional reverse osmosis operation is concentrated in the forward osmosis module from an initial concentration of about 70 grams per liter of total dissolved solutes to a final concentration, for example, 190 grams per liter, using a sodium chloride solution that is diluted from a higher concentration, for example, 207 grams per liter to a lower concentration, for example, 166 grams per liter as a draw solution. The diluted draw solution from the forward osmosis process is the feed for the first stage of the Suaro process. The water passes from the first stage to the last stage, as I have been explained in the previous slide, where the water is recovered in a conventional reverse osmosis stage. For a better understanding, the slide shows the first stage of the application. The inlet and outlet values, flow rate, and composition of the osmotic solution introduced in the first stage, as well as the hydraulic pressure of the high pressure chamber, can be chosen, knowing that the recent figures will affect both the number of stages and the membrane area to be required. In this example, some initial data have been chosen taking into account their ease of understanding without considering possible economical or energy optimization of the process. More specifically, the flow rate and the composition of the osmotic solution fed to the low pressure chamber in the first stage have been taken to be the same as the feed. At this stage, the brine contained in tank D1 is concentrated from a concentration of 166 grams per liter to a higher concentration of 207 grams per liter by regulating it through the high pressure side of the Suaro unit, where it is pressurized up to 75 bar. On the other hand, the low pressure chamber is fed with a solution of 166 grams per liter of sodium chloride. In other words, the feed is concentrated and the osmotic solution is diluted. This process is repeated in each step of the system until the last stage, where the water can be recovered from the diluted solution by means of a conventional reverse osmosis process. The main difference between the Swarrow and Swarrow processes, as can be seen, is that the Swarrow process works in a single reverse osmosis unit because the stages work sequentially. The total Swarrow process time will be the sum of the time used in each stage. Finally, I would like to conclude with a summary. Brines are generated in many industrial sectors under the management of various specific treatment systems. The brine concentrators that are commonly used require considerable energy consumption for their operation and significant capital investment in equipment. This method is designed to concentrate high-salinity brines that recover water with high energy efficiency and low investment cost in equipment, since only one osmotic assisted reverse osmosis unit and a series of tanks are necessary. In addition, the Swarrow operating variables, the time interval of each stage, the membrane area, and the necessary tanks can be optimized for each specific industrial application. Finally, we would like to point out that carrying out this work on an industrial scale directly influences the Sustainable Development Goal number 6, clean water and desalination, and contributes to the improvement of other sustainable development goals. Thank you for listening. If you have any questions, you can send me an email and I'll be happy to answer as soon as possible.
Thank you, Elena. So speaker is here. Otherwise, yeah, I'm very happy to sharing this session. So thank you for your support. And then next session is about the post presentation. So you can just access to your platform on the website, and then you can click the poster, and then there are 85 poster presentations, and around 25 you can utilize the video watching, so you can see the video presentation, as well as you can read some of the abstract. And then, yeah, if you can just communicate with the author, your email communication is possible. Also, you can leave your question to the in the box, so everything can be communicated through the poster presenters. So thank you for your supporting for today's session, and then I will see you in the poster session. Thank you.